And this time we'll be looking at the difference between sounds that are very loud and sounds that are very soft. In situations where we're talking to people, volume can be of a fair amount of importance. Turns out that if we're looking at wave terminology and how we describe waves, then we can describe the volume of a sound by looking at its intensity. So remember that intensity is a measure of how much energy a wave carries. So as you might have suspected, sound waves with more energy are much louder than sound waves with less energy. So the more energy a sound wave carries, the louder the sound wave seems. Now the intensity of a sound wave, as it turns out, depends on both the frequency of the sound wave and the amplitude of the sound wave, which makes things a bit complicated. So right now we're not going to be worrying about the frequency too much. Keep the frequency fixed, so the frequency is constant, which means that the intensity of the wave will depend on the square of the amplitude. So that means that if we increase the amplitude of a wave by a certain factor, its energy will increase by the square of that factor. This is as long as we're keeping the frequency of these two different waves constant. If we're looking at data from graphs, then this can be very helpful. You can see over here that I've got two graphs of waves, except one has twice the amplitude of the other. So how will that change its intensity? Well, a sound that has twice the amplitude, like over here, will have 4 times the intensity. This means that it will be 4 times as loud. Now, how do we measure volume? It turns out that we use a scale called decibels, which will be a little bit unusual at first. We have a graph here of how the intensity of a sound changes with decibels. On the x-axis, it's fair enough, 5, 10, 15, 20, so on. But hang on, look at the y-axis. We're going to 10, to 100, to 1,000. We're not going up by a certain number each time, we're going up by a certain factor. Every time we go up a step on the y-axis, we increase by a factor of 10. So that means that this point over here is not actually 0 on the y-axis. It's exactly 1, because that will be 1/10 of 10. The way that we talk about this in physics or even in mathematics is we say that decibels are a logarithmic system of measurement. Logarithms pertain to the different powers of numbers. So if we were to take the logarithm base 10 of the number 10, we'd get 1. If we were to take the logarithm base 10 of 100, we'd get 2. If we take the logarithm base 10 of 1,000, we get 3, and so on. So if one sound is 10 times louder, then it's 10 decibels louder. That's the conversion factor that we use. So that means that if we have two sounds and one is 10 decibels and one is 20 decibels, then the way that they will change in intensity is that the sound that has a loudness of 20 decibels will be exactly 10 times louder. So this is the conversion factor that we tend to use. This is in fact why we call the units decibels. Deci at the start of the unit comes from the old word for 10. So we have a set here of some different sounds and how loud they are. Something that has a volume of 0 decibels does not in fact have 0 intensity. It has 10 times less intensity than a sound that has 10 decibels. But the human ear is incapable of hearing sounds that have a volume of less than 0 decibels. So this is the limit of human hearing. 10 decibels is about the same volume as calm breathing, so it's very, very soft. 20 or 30 might be the sound of a quiet room. Getting a bit louder, about 40 decibels to 60 decibels is the volume of a conversation, with 60 getting into 70 being a fairly loud conversation. So at about 60 to 80, we get a moving car that's 10 meters away, or maybe the sound of a vacuum cleaner. At 80 to 90, which is 10 times louder, we're getting to the point where we have the sound of traffic. That's 10 meters away. So we can see that if we're further away from the source of a sound, it'll be softer than if we're very close to it. If we were to look at heavy traffic from only 1 meter away, it would be louder than 80 or 90 decibels, and it probably wouldn't be safe either. So what's louder than heavy traffic? A jackhammer is quite a bit louder than traffic. At least 10 times louder. Beyond that, we can get to things like jet engines, which get extremely loud. Even at 100 meters away, they're still louder than jackhammers. One of the very loudest sounds that we can experience is things at very close range, like a loud sound such as from a rifle, and only a meter away. Volumes around 140 decibels and 150 decibels are loud enough to give you permanent hearing damage over a very short time. In fact, the threshold of hearing damage starts somewhere around here, between 80 or 90. But for hearing damage to develop, you need to be exposed to that sort of sound for a very, very long period of time, in the order of 8 hours. So the sound that we hear in our ears, not exactly an accurate representation of intensity. Why would that be? Well, we've discussed before about infrasound and ultrasound, but it turns out that the human ear has different sensitivities for different frequencies of sound. When we get close to ultrasound or close to infrasound, and of course we can't hear those, then frequencies right in the middle. So what do you suppose the human ear is most sensitive to? Now, the human ear is most sensitive to the sound of other humans, as you might have expected.
Honored to be with you today for your commencement from one of the finest.
Speech has a frequency of about 3 to 4 kilohertz, give or take a bit, and so the human ear is able to pick these frequencies up more easily than any other set of frequencies. That means that even if a sound is very intense, if it has frequency that is much higher or much lower than 3 or 4 kilohertz, then it might not sound as loud as a different sound of the same intensity at those frequencies. The frequency and intensity of different sounds will determine how loud they seem to us. The loudest sound will be something with very high intensity and a frequency to right at the peak sensitivity of the human ear, 3 to 4 kilohertz. So if we're making things like hearing aids or hearing protection, then we need to make sure that they're able to compensate for the high intensity of different sounds, but especially at that point of greatest sensitivity, 3 to 4 kilohertz. Of course, because of the hearing damage that can occur at about 90 decibels and above, hearing protection can be quite important if, for example, you work with power tools all day. So that's the end of the theory for this section. We've talked a bit about the intensity of sound waves and the loudness of sound waves, as well as how we measure it and how it's affected by the human ear. So let's go on to some questions.